soft robots. Generally, soft robots, young field, the game is pretty open. Generally, what a soft robot is stands in contrast to what a hard traditional robot is. Instead of something that is created from a framework of linkages that are like connected by springs of a known K, instead they're dynamic systems. So sometimes mine are elastomeric, so they have internal chambers inside of a silicone, and the chambers are distorted and sort of causes total body distortion across the robot. Other ones are made of cloth. So Other Lab, a company in San Francisco, has robots that are made of kite fabric, and so the kite fabric rigidizes under pressure, and then they conditionally rigidize, they conditionally inflate and rigidize different aspects of it to get it to distort, almost like moving a parachute around. If you've ever seen a modern sail-type parachute, they distort the parachute to get the motion that they desire. Other places are using nitinol muscle wire. Other places are using pneumatic distortion inside of silicone-coated cloth. The general idea is to use compliant systems, systems that bend, that move, that have a dynamic movement, and get your motion from there. The idea being that you get advantages from tying mechanical systems together, like you find in nature, by having the mechanical systems also adapt to unknown inputs. And so instead of having a leg like Asimo does, which is placed exactly on a known spot where it's looking and it's testing, instead you have a leg that can conditionally handle some arbitrary input where it's like, there's a rock there, so the whole system, when it hits some imbalance, tries to self-balance because the way the mechanisms are tied together, not because it's absolutely being controlled by a visual guidance system and servos that are placing it right on the millimeter right there. So that's the sort of general framework of why soft robots. So this is the Empire soft robotic gripper that I was talking about. This is a jamming gripper. If you've ever bought espresso in the grocery store, it came vacuum packed and was a brick until you let the air in and it turned into a soft bag of material. What they're doing here is they have a jamming material inside of there. It's like a quartz sand, and they pull all of the air out when it's over top of something. And that form goes from a soft, squishy thing that's pressed over there and rigidizes. And so they rigidize it, and then it's stuck inside of the rubber until they let the air back in, and it turns into a soft, squishy rubber ball again.
I'm not sure I understand that. How does okay, you have the sand in the ball.
Yeah.
And you take the air out.
Yes.
But then how does this sandy ball? I understand how the sandy ball surrounds the brick. But how does it grab it? I mean, it seems to be that.
Yeah. So
you droop all over it, but then you like slip out.
Yeah. So it's a grippy enough rubber. So I haven't touched them, but from the demonstration, it looks like a squeaky, grippy kind of rubber. And so if they get over the sides, if the Lego brick had like draft on it, I'm guessing it would just drop out. But since it has straight sides, there's enough grip on it to pull up the Lego brick. For other things that they're gripping, they can get around it enough that they've actually got it locked in. And so the ball's soft enough that they can like squish their way over the return on an egg or a ping pong ball. Or like one of their demos is for a pair of scissors, just smushing it against the table. And by smushing the robot against the table, it actually gets underneath the scissors a little bit. So the general idea with this framework and how I tend to think about soft robotics and compliant mechanisms is you take arbitrary inputs and you can get it to good enough rather than taking an exact known input and getting it to an exact nanometer position. And so there are sort of two different frameworks for thinking about robotics. This one, very young, and there's a lot to still explore in it. Here are two of my robots, two of my more interesting complete experiments. So on the left is the quadruped I'm going to be demonstrating tonight. On the right is a tentacle called the treclo. It's sort of the easiest shape I could think of. Unfortunately, with a lot of the silicone casting stuff, the technology tends to look a little bit suggestive.
Okay, you're not actually controlling the circular motion, are you?
I mean, what?
Okay, in other words, I understand, I can see like three air things going out. I understand that you're inflating one diaphragm and then squeezing the other, but you're
Yeah.
not actually controlling this part of it. That's just something that happened.
It's actually, although it is not, small changes in wall thickness can change exactly how the tentacle moves. What I'm actually doing is I'm changing the duty cycle on each of the air chambers, and so I can control how inflated they are. And so 50% this one and 50% this one, the combined direction is over there, and then I can change the duty cycle to get a relatively precise position. It's not precise like a rotary encoder, but I can stop at a particular spot if I just maintain that particular duty cycle. And so I can go to an address and just say like, no more inflation, you're good. It's not like a precision machine, partially because the dynamics of inflating skins like this are very influenced by things like wall thickness, because the way the system finds equilibrium, a small bubble can actually change how this chamber, with the exact same amount of pressure, bends a little bit more, has a little bit of twist to it, because it bends away from where that distortion is happening. But once it's assembled and moving, it's actually relatively easy to sort of roll back and be like, okay, this is the behavior of this guy. It's relatively easy to just be like, okay, I'm just going to plot that, and now it's just a button on a screen.
Yeah, but how repeatable is it from time to time?
From any two tentacles, it's not repeatable, but on this tentacle, the same duty cycles get you to the same spot. And I'm not doing like precise measurements of it, so how close it is any two times is difficult.
How much force can one of these things exert?
So I have some experiments with ones with spines in them, so that they don't extend. So what happens with this guy is it actually grows taller, in addition to growing the size increasing in their surface area. And so if you put your hand against it, it'll put like a pound of force against you, and then it'll get backed up into the system, and the thing will keep inflating and inflating.
Right.
So rather than pushing harder against you, it's actually inflating itself to sort of keep itself in the same spot. With spines, it yields more force because that dimension of it's sort of like if you have a balloon inside of a closed container. The bigger the balloon starts, the more pressure gets pushed onto the container because less is being pushed onto the balloon. It's a similar deal with the spines in them. Orienting things inside of these guys is sort of a dark art, but with spines in them, they push more force, but it's only about a pound from the trapdoor tentacle.
So it's structurally how you figure out how to design the spines or other internal supports.
Yeah.
To focus the force in that direction.
Yeah. Essentially, the mechanisms that I'm using, the rigged ones, essentially the air is causing a distortion lateral to the rib. It's almost like, like electricity and magnetism. It's like at right angles to the structure. And so that's creating an extension in the amount of surface area there, and that's creating the bend. By limiting certain dimensions from being able to bend, you get, and not a force multiplier, but you can control where the force is delivered by limiting how it's extending in various directions. So like putting a piece of string in the robot, like something as simple as putting a piece of string in can stop it from moving in that particular direction. All of the force has to move in other directions, which can be sort of a force multiplier.
About how many pounds of air pressure can you put in these
These
things?
guys, so I'm going to do a demo in just a second to show you. It's about 2 psi, 2 to 3 psi is where most of these guys are working at. There are higher pressure paradigms, but a lot of the stuff I'm getting the activity I want, sort of with the lowest amount of pressure that I can. Different materials, there is no reason why you can't get higher pressure. It's just these happen to work at low pressure. So I also was the roboticist for a company called Bond, making computer-controlled note writing machines. So I have a bit of a traditional CNC robotics background. These were machines intended to get your handwriting delivered to anyone, anywhere in the world. So the idea is you go